All right, let's dive into one of the wildest truths about our universe. The faster you move through space, the slower you actually move through time. It's a real thing called time dilation. And believe me, it's not science fiction, it's just how reality works. So let's start with a really basic question. Is a second for you the same as a second for me? For almost all of human history, everybody would have said, of course. Time was this giant cosmic clock in the sky, ticking away at the exact same rate for everyone, everywhere. But as we're about to find out, reality is a whole lot stranger than that. So the first real crack in that idea of a universal clock came way back in 1905 from Albert Einstein. In his theory of special relativity, he basically said, hey, what we see and measure actually depends entirely on how we're moving relative to each other. This one little idea that your point of view changes what you observe was about to completely blow up our understanding of space and time. Now, to build this new theory of his, Einstein didn't start with a bunch of crazy, complicated math. Nope, he started with just two beautifully simple ideas. He called them postulates that he just declared were true. And from these two simple rules, everything else, well, it just falls into place.
And here they are. Okay, the first one, pretty straightforward. The laws of physics, gravity, electromagnetism, they don't just change because you're on a train moving at a constant speed. Makes sense, right? But that second one, that is the bombshell. It says the speed of light is always the same. Always. It doesn't matter if you're standing still or flying in a spaceship at half the speed of light. If you measure a light beam, you get the exact same speed. This is where common sense just completely goes out the window.
So, to really explore the bizarre fallout from this cosmic speed limit, Einstein used one of his favorite tools, a Gedanken, which is just German for a thought experiment. He imagined the simplest, most perfect clock you could possibly build, a light clock. Okay, so picture this. You've got two mirrors facing each other, and between them, you have a single pulse of light, just one little photon, bouncing back and forth. Every time that photon hits the top mirror, let's say, the clock ticks. It's simple, it's elegant, and it's perfectly reliable because its timing is based on the one thing we now know is constant for everyone in the universe, the speed of light.
All right, now let's put our perfect clock on a train. If you're on the train, moving right along with the clock, what do you see? Well, nothing special. The little light pulse just goes straight up, hits the mirror, and comes straight down. A simple vertical path. Tick, tock. Easy enough.
But, and this is the big but, what about for someone standing on the station platform, watching that train whiz by? From their perspective, the clock is moving. So in the time it takes the photon to get from the bottom mirror to the top one, that top mirror has actually moved down the track. So to catch up, the photon can't go straight up, it has to travel a longer diagonal path to get there. And right there, that's it. That's the absolute core of the idea. This is the aha moment, where Einstein's two simple rules collide and force us to accept a brand new, startling reality. Okay, let's just walk through the logic here because it's inescapable. We know from postulate number 2 that the speed of light has to be the same for the person on the train and the person on the ground. But we just saw that for the person on the ground, the light has to travel a longer diagonal path. So, think about it. If the speed is the same, but the distance is longer, what's the only thing that can possibly give? Time itself. Time has to slow down for the moving clock to make the math work. Each tick literally takes longer to happen. And this bizarre, mind-bending effect has a name, time dilation. And it's not some trick of the clock, it's not a mechanical error, it's a fundamental property of time. To a stationary observer, any clock that's in motion will genuinely appear to be ticking slower. Okay, I know what you might be thinking. This sounds like a really clever brain teaser, a neat philosophical puzzle. But is it real? Does this actually happen out here in our universe? Well, as it turns out, we have a ton of proof, from tiny little particles to jumbo jets. So, let me introduce you to a particle called the muon. It's a tiny elementary particle, and when you have one sitting still in a lab, it has a really short life. It has a half-life of just 2.2 microseconds. That's 2.2 millionths of a second. Then poof, it decays into other stuff. Now, even moving at nearly the speed of light, a muon with that tiny 2.2 microsecond lifespan should only be able to travel about 660 meters, max, before it disappears. Just remember that number. 660 meters. And here's the puzzle. These muons are being created constantly, way up in our atmosphere, about 8,000 meters up, when cosmic rays smash into air molecules. So, if they can only travel 660 meters, we should never, ever see one down here on the ground. But we do. We detect them all the time. So how is that possible? Time dilation. From our point of view on Earth, their little internal clocks are running incredibly slow. That 2.2 microsecond half-life gets stretched out, giving them more than enough time to survive the long trip down to us. But we don't have to just rely on particles from space. In 1971, two physicists, Joseph Hafele and Richard Keating, decided they were going to test this thing directly. They took several incredibly precise atomic clocks, synchronized them perfectly, left one on the ground, and put the others on commercial airplanes to fly them around the world. And when the planes landed and they compared the clocks, the results were just astonishing. The clocks were no longer in sync. The ones on the planes had measured a different amount of time passing, and the amount they were off matched Einstein's predictions almost perfectly. This wasn't a thought experiment anymore. Time dilation was a real, measured, physical fact. So this isn't just some weird academic curiosity. Time dilation has very, very real consequences, and it is absolutely essential to the technology that many of us use every single day. Just think about the GPS in your phone or your car. It works by talking to satellites that are whipping around the Earth at thousands of kilometers an hour. Because they're moving so fast, their clocks tick just a tiny bit slower than ours down here on the ground, only by about 7 microseconds every day. It doesn't sound like much, right? But if the engineers didn't constantly correct for that tiny difference, the GPS system would fail. Your location would drift by about 10 kilometers every single day, making it totally useless. Time dilation also gives us the ultimate speed limit in the universe. See, the faster you go, the more extreme time dilation becomes. From an outside perspective, your clock would seem to slow down, approaching a near stop as you get closer and closer to the speed of light. To push you even a little bit faster would take more and more and more energy. To actually hit the speed of light, your time would have to stop completely, and that would require an infinite amount of energy. So it's just not possible. Time dilation itself is the cosmic traffic cop. So we kind of end where we began, with a question. We've just seen that time, something we all feel is constant and absolute, isn't. It's flexible, it depends on your point of view, on how you're moving, and it really makes you wonder, doesn't it? If time itself is relative, what other big fundamental ideas about reality might not be quite as solid as we think they are?